It is a universal experience, the most fundamental sensation of our existence. We feel it in the steady beat of our hearts, in the turning of the seasons, and in the lines that map the stories upon our faces. It is the river that carries us from birth to death, a current so powerful and so persistent that we rarely stop to question its direction. But what if we did? Imagine a cup slipping from your grasp. It falls, it shatters into 100 pieces on the floor. You can rewind a film of this moment and watch the shards miraculously leap from the ground, reassembling themselves perfectly into your hand. But you will never witness this in reality. You will never see the spilled milk gather itself from the table, or the smoke from an extinguished candle funnel back into the wick. Our experience screams at us that this current, this flow we call time, is a one-way street. The past is a fixed landscape of memory, the future an undiscovered country of possibility, and the bridge between them, the present, moves in only one direction, from yesterday towards tomorrow. This is the arrow of time, but in the pristine, elegant mathematics that describe our universe, this arrow is strangely absent. The fundamental laws of physics, from the grand cosmic dance of galaxies to the frantic waltz of subatomic particles, seem to work just as well backwards as they do forwards. They are symmetric in time. So where does this profound asymmetry, this relentless, irreversible march into the future, come from? Why does the cosmos forbid us from turning back the clock? The answer is not found in a single law, but is woven into the very fabric of existence, from the birth of the universe to its ultimate, distant fate. It is a story of order, chaos, and the profound power of probability. For centuries, our conception of temporality was simple, almost intuitive. The ancient Greeks, like the philosopher Heraclitus, saw existence as an ever-flowing river. No man ever steps in the same river twice, he mused, for it's not the same river, and he's not the same man. Time was change, a perpetual state of becoming. This poetic idea was given a rigorous, mathematical foundation by the titan of classical physics, Sir Isaac Newton. In Newton's universe, time was absolute. It was a grand, cosmic metronome, ticking at a constant, unwavering rate for every observer, everywhere in the cosmos. It flowed equably without relation to anything external. This absolute chronology was the backdrop against which the drama of the universe played out. The planets moved in their predictable orbits, projectiles arced through the air with mathematical certainty. The universe was a magnificent clockwork mechanism, set in motion by a divine clockmaker. And in this deterministic world, if you knew the precise position and momentum of every particle at one instant, you could, in principle, calculate the entire future and reconstruct the entire past. The equations governing this clockwork cosmos were time-symmetric. Running them backwards simply described the same events in reverse. There was no inherent direction, no built-in arrow. The shattering cup and the reassembling cup were equally valid solutions. Yet, this perfect, reversible clockwork model could not explain the most obvious feature of our world, the irreversible reality of decay, of aging, of things falling apart. The answer would not come from the pristine orbits of the heavens, but from the grime, smoke, and thunder of the Industrial Revolution. The 19th century was an age of steam and steel. Engineers were building powerful machines to drive factories and locomotives, and in their quest for greater efficiency, they stumbled upon a new, fundamental truth about the universe. They were developing a new science, thermodynamics, the study of heat and energy. They discovered that energy could be converted from one form to another, but never created or destroyed. This was the first law. But they also discovered a more subtle and far more profound second law. Every time energy changes form when coal burns to produce steam, or steam pushes a piston, some of it is inevitably lost as waste heat. It dissipates into the environment, becoming unusable. You can't gather all that dispersed heat and use it to reconstitute the original lump of coal. The process is irreversible. This simple observation about the inefficiency of steam engines held the key to the arrow of time. In the 1850s, the German physicist Rudolf Clausius formalized this idea with a new, mysterious quantity he called entropy. Entropy, in essence, was a measure of the disorder or randomness of a system. The second law of thermodynamics states that in any isolated system, the total entropy, the total amount of disorder, will always increase or, at best, stay the same. It can never decrease. The universe, as a whole, is moving from a state of order to one of disorder. This law explains why a hot cup of coffee cools down. The ordered state is having all the fast-moving, high-energy molecules concentrated in the cup. The disordered state is having that energy spread out evenly throughout the room. Energy naturally flows from hot to cold, from order to disorder, increasing the total entropy of the room. It explains why buildings crumble, why organisms decay, and why memories fade. The arrow of time, it seemed, was the arrow of increasing entropy. The universe has a clear and unambiguous direction. It is a one-way slide into chaos. But this raised an even deeper question. Why? Why should the universe favor disorder over order? The answer would come from one of the most brilliant and tragic minds in physics, an Austrian genius named Ludwig Boltzmann. Boltzmann was not content with merely stating that entropy increases. He wanted to understand why times it increases. He proposed a radical idea. He imagined that all matter was composed of countless tiny atoms, colliding and jostling according to the simple, time-symmetric laws of mechanics. From this microscopic, mechanical world, he sought to derive the irreversible second law of thermodynamics. Boltzmann's great insight was that entropy is not a fundamental force, but a matter of statistics and probability. Disordered states are simply vastly more probable than ordered states. To grasp this, consider an analogy. Imagine a brand new deck of cards arranged in perfect sequence, ace to king for all four suits. This is a state of very low entropy, a state of perfect order. There is only one way for the cards to be in this specific sequence. Now, shuffle the deck. The cards become jumbled. This is a high entropy state, a state of disorder. What are the odds that if you keep shuffling, the cards will spontaneously return to their original, perfect sequence? The number of possible ways to arrange 52 cards is an astronomical figure, roughly 8 followed by 67 zeros. It is a number far greater than the number of atoms in our galaxy. There is only one perfectly ordered arrangement, but there are countless trillions upon trillions of disordered arrangements. Every shuffle lands you in one of these overwhelmingly numerous disordered states. It is not physically impossible for the cards to fall back into perfect order, but it is so statistically improbable that you would have to shuffle for trillions of years, longer than the current age of the universe, to have even a remote chance of seeing it happen. Boltzmann argued that this is precisely what happens with the atoms in the universe. There are vastly more ways for atoms to be arranged in a disordered, high-entropy configuration than in an ordered, low-entropy one. The universe isn't being pushed towards disorder by some mysterious force. It is simply evolving, through the random collisions of its constituent parts, from an incredibly unlikely state of low entropy into an overwhelmingly more probable state of high entropy. The arrow of time is the universe's journey from the improbable to the probable. The shattering of the cup is a journey from a single, ordered arrangement of atoms into one of the countless trillions of disordered arrangements of shards. The reverse is statistically forbidden. Boltzmann's ideas were revolutionary, but they were met with fierce resistance. Many of his contemporaries in the scientific establishment refused to believe in the existence of atoms, let alone his statistical interpretation of reality. They pointed to the time-symmetric nature of the underlying mechanics and argued that for every process moving towards disorder, a reverse process should be equally possible. Tormented by this scientific rejection and his own failing health, Ludwig Boltzmann took his own life in 1906, never living to see his atomic theory and statistical mechanics become the cornerstones of modern physics. His tombstone is etched with his great equation, S equals K log W, forever linking entropy S to probability W. It is a tragic and profound epitaph for the man who explained time's arrow. Boltzmann's statistical explanation provides a powerful reason for why time flows one way, but it hinges on one enormous, universe-sized assumption. It requires that the universe began in a state of extraordinarily low entropy. Like our deck of cards, the cosmos must have started in a state of near-perfect order. But just as this explanation was taking hold, another revolution was brewing, one that would completely transform our understanding of space and time itself. The young Albert Einstein, working as a patent clerk in Bern, Switzerland, was about to shatter Newton's clockwork universe forever. In 1905, Einstein published his theory of special relativity. Its consequences were mind-bending. He demonstrated that there is no absolute time, no universal cosmic metronome. The rate at which time passes is relative. It depends on your motion. For an astronaut traveling near the speed of light, time would slow down dramatically compared to an observer on Earth. This time dilation is not a trick of perception, it is a real, physical effect. Clocks aboard fast-moving GPS satellites must be constantly corrected. To account for this relativistic slowing, or their navigation systems would fail within minutes. 10 years later, with his general theory of relativity, Einstein went even further. He showed that space and time are not separate entities, but are woven together into a single, four-dimensional fabric, space-time. Massive objects like stars and planets warp and curve this fabric, and this curvature is what we experience as gravity. The Earth is not being pulled by the sun, it is following the straightest possible path through the curved space-time created by the Sunday. This new picture of reality has staggering implications for the nature of time. If space and time are part of a single continuum, then time is much more like a spatial dimension. This leads to a model of the universe known as the block universe, or eternalism. Imagine a loaf of bread. Each slice of the loaf represents the state of the universe at a particular moment. The first slice is the Big Bang, the last slice is the ultimate future, and all of history is laid out in between. In this view, the past, present, and future all exist simultaneously. They are all equally real. The Big Bang is not an event that times happened times and is now gone. It is a location in space-time, just as your birthplace is a location in space. The future is not an unwritten realm of possibility. It is already there, a fixed landscape further down the block of space-time. Our sense of the flow of time in this model is an illusion. Our consciousness simply moves along the time dimension of this block, experiencing one slice after another, creating the sensation of a moving present. The distinction between past, present, and future is merely a stubborn, persistent illusion of human perception. But if the entire history of the universe is a static, unchanging block, where does the arrow of time, the sense of direction, come from? Even within this static block, there is still a clear structure. The slices are arranged in a specific order, an order dictated by entropy. The slice corresponding to the Big Bang has incredibly low entropy. Slices corresponding to the distant future have incredibly high entropy. So while the block universe does away with the flow of time, it preserves the arrow of time as a fundamental asymmetry. Built into the structure of space-time itself, the universe is ordered in one direction and disordered in the other. Our consciousness, our lives, our very psychological experience of time is oriented to perceive this direction of increasing entropy. We remember the past, the lower entropy state, and we anticipate the future, the higher entropy state. Einstein's relativity provided a new stage for the cosmic drama, but Boltzmann's statistical law remained the star of the show. The arrow of time was still the arrow of increasing disorder. However, as physicists began to explore the universe at its smallest scales, they discovered a new realm where the rules of reality seemed to defy all classical intuition. The world of quantum mechanics presented a new and baffling paradox. At the subatomic level, The world is a storm of probabilities and uncertainties. Particles can be in multiple places at once, they can tunnel through impenetrable barriers, and they can be mysteriously linked across vast distances. Yet, for all this strangeness, the fundamental equations that govern this realm, like Schrödinger's equation, share a key feature with Newton's laws. They are perfectly time-symmetric. A film of two electrons colliding and scattering looks perfectly plausible, whether you play it forwards or backwards. There is no inherent arrow of time in the basic interactions of matter. This creates a profound disconnect. How can a macroscopic world, which is built from these quantum components, exhibit such a powerful, irreversible arrow of time when its fundamental constituents operate by reversible rules? It's like building a one-way street out of cars that can drive equally well in either direction. One of the deepest mysteries in quantum physics, the measurement problem, may offer a clue. In the quantum world, a particle exists in a cloud of possibilities, a superposition of all its potential states, described by a wave function. But the moment we try to measure it to observe its position, for example, this cloud of possibilities inexplicably collapses into a single, definite outcome. This act of measurement, this interaction between the quantum system and the large-scale classical world, seems to be an inherently irreversible process. You can't unmeasure a particle and restore its original cloud of possibilities. Some physicists believe that this process of wave function collapse is where irreversibility, and thus the arrow of time, first enters the physical world. It is the bridge between the ghostly, time-symmetric quantum realm and the solid, time-asymmetric reality we experience. Another idea, known as quantum decoherence, suggests that the arrow of time emerges from the way a quantum system interacts and becomes entangled with its vast environment. A single, isolated quantum system can maintain its time-reversible behavior, but as soon as it interacts with the billions upon billions of particles in its surroundings, information about its initial state leaks out and becomes hopelessly scrambled throughout the environment. Trying to reverse the process would require tracking and reversing the state of every single particle in that environment, a task of impossible complexity. In this view, irreversibility is an emergent property born from the sheer complexity of the macroscopic world. The quantum realm adds layers of immense complexity and mystery, but ultimately, all roads lead back to one monumental question. Whether we are talking about Boltzmann's statistics, Einstein's spacetime, or the mysteries of quantum collapse, every explanation for the arrow of time relies on a single starting condition: that the universe began in a state of extraordinarily low entropy, a state of unbelievable order. This is what cosmologists call the past hypothesis. The arrow of time is not a law of physics in itself, but rather a consequence of the specific initial conditions of our cosmos. Our universe didn't just happen to start, it started in a very, very special way. All the evidence we have points to a beginning, some 13.8 billion years ago, in an event we call the Big Bang. At this moment, the entire observable universe, all the matter and energy that would eventually form trillions of galaxies, was compressed into a space smaller than an atom. It was a state of unimaginable density and temperature, but also, paradoxically, of incredibly low entropy. How can a hot, dense fireball be considered ordered? The key is gravity. In the early universe, matter was spread out almost perfectly smoothly. This smooth distribution was a state of low gravitational entropy. Gravity is an attractive force. It pulls things together. Over cosmic time, it has pulled that smooth gas into dense clumps, forming stars, galaxies, and black holes. This clumpy, structured universe we see today is actually in a state of much higher gravitational entropy than the smooth, primordial fireball of the Big Bang. The Big Bang was the cosmic equivalent of a perfectly assembled, unshuffled deck of cards. The entire subsequent history of the universe, the formation of structures, the burning of stars, the evolution of life, has been the process of this cosmic deck being shuffled, relentlessly increasing the total entropy. So, the ultimate question of why time flows forward becomes the question of why the universe began in such a special, low-entropy state. And on this question, physics currently has no definitive answer. It is perhaps the greatest mystery in all of science. Why wasn't the universe born into a state of maximum entropy, a chaotic equilibrium? Why did it start with this immense potential for interesting things to happen? Some physicists speculate that our Big Bang might be just one event in a much larger multiverse, and that we simply find ourselves in one of the rare, ordered pockets capable of supporting life. Others propose models of a cyclical universe where our cosmos could have emerged from the collapse of a previous one. But for now, the low-entropy beginning of our universe remains an unexplained, brute fact, the ultimate source of every broken cup, every memory, and every tick of the clock. This cosmic story, which begins in primordial order, also points towards an ultimate destiny. If the arrow of time is driven by the inexorable rise of entropy, what happens when entropy can rise no further? The second law of thermodynamics paints a stark, desolate picture of the universe's far future. Trillions of years from now, all the stars will have burned out. The galaxies will be populated by the cold, dead remnants, black dwarfs, neutron stars, and wandering planets. Over even more immense timescales, quantum effects will cause even these remnants to decay. Black holes themselves will eventually evaporate through a process known as Hawking radiation. Eventually, after a span of time so vast it defies human comprehension, the universe will approach a state of maximum entropy. It will be a thin, uniform soup of elementary particles and low-energy radiation drifting aimlessly through an ever-expanding, near-empty space. This is the heat death of the universe. In this final equilibrium state, there will be no temperature differences, no structure, no available energy to drive any process. Nothing will happen. And if nothing happens, if there is no change, does time itself still have meaning? In a universe of maximum disorder, the arrow of time would cease to exist. There would be no distinction between past and future. Chronology itself might dissolve into a timeless, featureless void. It is a sobering, and perhaps terrifying, vision of ultimate stillness and silence. So we are left with a profound and beautiful portrait of our existence. We live in a fleeting, precious epoch of the universe's history, a period between the fiery order of its birth and the icy chaos of its death. The arrow of time, this one-way flow that we find so intuitive, is a consequence of that special beginning. It is the unwinding of the cosmic spring that was coiled at the Big Bang. It is the sound of the universe shuffling its cards, moving from its most improbable state to its most probable one. This cosmic arrow provides the direction for everything we know and experience. It allows for the formation of complex structures like stars and planets. It allows for the process of evolution, the gradual accumulation of information that creates life. It allows for the mechanisms of memory in our brains, the laying down of ordered neural traces of past events. Our very consciousness, our sense of self, journeying through a sequence of moments, is intrinsically tied to this thermodynamic flow. We are creatures of entropy. We are born, we live, we age, and we die, all surfing this relentless cosmic wave of increasing disorder. The refusal of time to flow backward is not a minor inconvenience. It is the fundamental rule that makes the universe interesting. It is the reason there is a difference between cause and effect, between a memory and a dream. It is the canvas upon which the entire story of the cosmos is painted. While we may never be able to mend the shattered cup or turn back the clock of our own lives, we can find a deep sense of wonder in understanding why. We are witnesses to a universe in the process of becoming, a universe unfolding from a beginning of exquisite order, powered by the inexorable march of time's arrow on its grand, one-way journey into the endless future.